Okay, for chapter 10, I'll mention the concepts real quick. Remember, these are things that you need to go back and read. I'm not covering them in detail here. I'm just pointing out these are some good places to go back and look at our slides and go through your notes. First, we have the definitions of enthalpy, heat, work, and temperature. Remember, these were a bunch of different concepts we used about things about how energy moved around and how molecules moved and a bunch of other stuff. So you want to go back and look at these and make sure you can differentiate between a definition. For example, what's heat versus what's work, what's heat versus temperature, and what's an enthalpy. You should have an idea of what those all mean. Remember also that within enthalpy, it's the idea specifically of what's a state function. And why is enthalpy a state function? What does it mean that it is, and why is it? But then heat and work aren't state functions. So what does that mean? We then have the idea of conservation of energy. That one we both use conceptually and through problems. It's just the energy doesn't just disappear. It has to go somewhere. So if we lose energy in our reaction, it has to, in our system, has to go into our surroundings. We then follow up with the idea of how heat flows. In a very general sense, it's the idea that hot things, the heat is going to go from them into the colder thing if they're in contact. We don't hold water in our hand and suddenly have it freeze into an ice cube. But we do have an ice cube melt in our hand because our hand is warmer than the ice cube. So heat is able to flow from the hand into the ice cube. But we can't suddenly make the ice cube really cold by holding it unless somehow our hand were below freezing, which if you're a person, that's not happening. Or you're dead. That'd be bad. So you can't freeze stuff by holding it unless something is very wrong with the temperature inside your hand. Okay. Also remember from that, and it will also help with the next definition, endothermic versus exothermic, is what systems and surroundings are. Remember, systems is like our thing we're studying, and then surroundings are the stuff that we're going to that are going to be around our system. So if some change happens in the system, so let's say we've got our ice cube we're studying, or maybe we've got our metal block that we've got put in water, that piece is our system. Anything that happens to it in terms of heat and temperature flow, the opposite is going to happen to the surroundings, the stuff around it. So if I put my hot piece of metal into some water, and the metal is my system, that metal is going to suddenly lose energy as it goes into the water. But the water as the surroundings are going to absorb that energy because the metal couldn't just lose it and have it disappear according to the conservation of energy. So be okay with the idea of systems and surroundings and defining those. Then we have endothermic versus exothermic reactions. This is mostly make sure you're okay with the terminology. If I have an endothermic reaction where I mix some powder in with the water and it's endothermic, be able to tell me, should the cup that I'm holding that's got the water in it feel cool or should it feel warm? And where is the energy going and where is it coming from? So what releases energy, what absorbs it in each case. And then finally, Hess's law. You should be able to work from something like enthalpies of formations or energy of bond formations or tables like that. How much energy is going to happen for a reaction even if you don't know that exact reaction and don't have experimentation for it? What type of estimate can you make for what the energy change probably is using the fact that enthalpy is a state function and some information you have about different formations or different bond energies? So let's try doing some problems now. So first, some heat capacity stuff. We'll start with something that's kind of straightforward, I believe. How much heat is absorbed by a 50-gram piece of aluminum if it is heated from 0.00 degrees Celsius to 25.0 degrees Celsius? If you worked the problem in a previous version of my slides, if you've already worked it before seeing this, you may not have quite as many sig figs written in there, and that's okay. I added those to make sure, yes, this is a problem where I'd like 3 sig figs. But if you did the version where there's only 1, that's okay too. So we want to know how much heat is being transferred. We're going to use our Q equals MC delta T. We're only dealing with one system. We only know stuff about the aluminum. And we know we want to find the heat. So there's going to need to be a Q in it. So some of our other equations don't help us because they don't have a Q in them, actually. So we now know that Q is equal to 50.0 grams because that's the mass of my aluminum. We then have the specific heat, which we can go over to our handy-dandy table and find. Woo! Remember, you'll have that on the back of your exam, but you do have to be able to find it on there, so don't forget to look it up. It's not that I forgot to tell you. It's that I already provided to you. It's just on the back. So we have 0.903 joules per grams times degrees Celsius. We then finally have our delta T. So that's TF minus TI. So the final temperature is 25 degrees, and the initial temperature is 0.00 degrees. So it's going to, 25 minus 0 will give us 25. So then we're going to multiply these together. Our 50 times our 0.903 times our 25. And we are going to get that this has an energy change equal to 1,130 joules. Remember, this is, in this case, positive. So if there were two answers, there's a negative and a positive, this would be positive. And that makes sense because our temperature is going up, and we're asking how much heat is absorbed. So it is gaining the energy. Our system is gaining something. Let's look at another example. So that's our first one. We just use Q equals mc delta T. So if it takes 11.8 joules to heat a 10-gram piece of material 5 degrees, what is the specific heat of the metal? So I'm telling you it's a metal of some type. Which of the substance listed at the right is the most likely identity for the material in question? So now, we know something about the energy this time, so we're still going to use our Q equals mc delta T. But now we're going to rearrange it because we know delta T, we know mass, and we know Q. But we don't know C. So we can rearrange this as C equals Q over m delta T. Hopefully you notice I just divided by m delta T. And then I like having the thing that I want by itself on the left, so I just reverse the order I put them in. Remember, x equals 2 is the same as 2 equals x. Same idea here. So now we'll put our values in. Our Q was equal to 11.8 joules. It tells us at the top. We then know our mass. This is a 10-gram piece of material, even though we don't know what it is. We know it's mass. And this time you were told the delta T directly, rather than being given two temperatures. And this time it tells you that you're going to heat a 10-gram piece of material 5 degrees. So we're saying we're going to heat it up. That's going to be an increase in temperature. If we're increasing it, that means it's going to be positive T. And if it decreased in temperature, if I told you cooled it down, it would be negative. So plus 500 degrees Celsius. And you'll notice the units work out for specific heat as well. There's a joule on top and a gram and a Celsius on bottom. So we put these numbers in. 11.8 divided by 10 and divided by 5. And we're going to get that this has a specific heat of 0.236 joules per gram times degrees Celsius. So that's the answer to the first question. The second question was, which of these substances is likely the identity of the material in question? So as we look through these, silver is by far the closest. Nothing else really comes close. So I'm going to say that I think this is silver. So for some reason, I knew it was one of these. And within that, silver definitely seems like the most reasonable answer. Okay. Now let's look at one more question. This one's going to have a little bit more math to do, but otherwise it's using a fairly similar idea. We have a 25-gram block of silver. It's heated up at 98 degrees Celsius. That means that's where it's starting. And it's submerged into 125 grams of water at 20 degrees Celsius. What's the final temperature of the system at thermal equilibrium? So here I have information about two different systems I want to know. So this is a good choice that I'm going to try using. mc delta T equals negative mc delta T. And remember, it doesn't matter which material you put on which side, but just make sure you're consistent. So if I do silver on the left for the mass, that also needs to be for the temperature of the specific heat. As long as you're consistent, the materials can go either direction. The idea being that if you were just to divide the system by -1 or multiply by -1, both doing the same thing, it would simply reverse the negative so that what was on the left instead of on the right. So it doesn't matter which you put there. The rest of the signs in the problem will take into account if the negative's on the right or the left. Just don't forget it, and don't put it on both sides, and don't suddenly change which metal you're talking about on one side. Okay, so I am going to go with, our left is going to be our silver. So we're going to have a 25.0 gram block. I'm not going to. For this one, because of how much size I have, I'm not going to worry about writing this stuff, because otherwise I will not be able to reasonably fit it on what we're looking at. So we have 25.0. We're going to go to the specific heat. We have to look it up on the right. For silver, it's going to be 0.235. For our delta T, we don't know TF, so we just have to put TF. But we know it's going to start at 98.0 degrees. So we're going to set this equal to our negative sign. Don't forget that. 125 grams. We're then going to have that it's got a specific heat for water of 4.18. And then we're going to have our temperature change. Again, we don't know the final temperature, but we do know that it starts at 20 degrees Celsius. Okay, now let's do some multiplication. We're going to have to do a few times with a bit of algebra for this one. So first we do 25 times 0.235, and we're going to get on this side that we have 5.875 times TF minus 98.0 is equal to negative 522.5 times TF minus 20.0. You'll notice all I did was multiply the two numbers up front. So now what I need to do is I need to distribute over my parentheses. So that means you're going to multiply both numbers by the one on the outside. So we're going to have 5.875 TF minus, let's see, that'll be 575.75. That's going to be equal to negative 522.5 TF. And remember, the negative is going to cross over to both. So a negative times a negative with this 20 degrees is going to create a positive. So we have a positive 10,450. Now, the numbers may look a little big, but this would be just like if we had something like x minus 2 equals 2x plus 6. We just have to isolate our variable. So we're going to move all the TFs to the left and all the other numbers to the right. So I add 522.5 to both sides, and we're going to get 528.4 TF. I'm then going to add 575.75 to both sides, getting rid of it on the left, and I will get this is equal to 11,026. Then all we have to do is we can divide both sides by 528.4. So we are dividing by 528.4 on both sides. This will get it so we have the TF by itself, and this will get us to a TF equal to 20.9 degrees Celsius. And as a good check, we see that this temperature falls between the 98 of our silver and our 20 of our water. If it had fallen below 20 degrees or above 98, that means we would have a problem because I can't put something hot into something cool and make it colder. And I'm not going to put something hot into something cool and make the heated material actually increase in temperature. It has to go so that as long as there's not a chemical reaction or something taking place, it's got to be between the two. So assuming it's just heat transfer and we're not worried about some reaction. So that's really going to cover a lot of the stuff we do with heat capacity. So let's look at another problem where we do some enthalpy calculations. Or wait, I forgot I did have this calorimetry problem I wanted to ask. Well, but yeah. So we're going to have a calorimeter. We're going to have 25 milliliters of 0.1 molar HCl and 25 milliliters of NaOH. The temperature of the solution is going to increase by 7.5 degrees Celsius. I want us to calculate the enthalpy change for the reaction, and we give you some numbers to use for the density of the solution and the specific heat. So what I need to figure out first is what's happening. What's the reaction I want to find the enthalpy for? So I want to make sure I know what the balanced chemical equation is. So HCl plus NaOH, if we remember from our last exam, it's an acid plus a base. It's going to make water plus NaCl. And if you check all the atoms, this is indeed a balanced chemical equation. So now I need to know how many times this reaction is going to happen. So what's the limiting reactant in this problem? So we figure out from the fact that we have 25 milliliters and 0.1 molar HCl, we should be able to get that we have 0.00250 moles of HCl, and that we have 0.00250 moles of NaOH. I got this from multiplying my molarity times my volume after changing my volume into liters. If this is something that made you go, whoa, how'd you do that? You might have to go and look back at my video on how to do molarity calculations, because at this point I'm going to have to assume that you can get through that part and it won't be too hard for you. Because this wasn't a very complicated molarity question. It was just, here's a volume, here's a molarity, how many moles? So hopefully this should be reasonably comfortable. If not, that's something you want to go back and look at. So we know that this is a one-to-one reaction, so each of these are present in exactly the right amounts. So it doesn't matter what I use for my limiting reactant, they're both going to run out at exactly the same time. So now I know how many moles of reactions are going to occur. This reaction is going to happen 0.00250 mole times. That's how many times I'm going to get the reaction. So that's how much sodium chloride I'm going to make, for example. So now what I want to know, though, because I want to find my enthalpy, is I want to know how many joules of energy were made when we tested this reaction, or how many got released from this reaction. Or how much did it absorb? We've got to figure that out. Well, we know the temperature of the solution increases by 7.5 degrees Celsius. That's a good hint that this reaction is going to release energy. If it had done it the other way, it would have absorbed energy if it got cooler. So, to be able to figure out how much energy, though, was associated with that release, we can go with Q equals mc delta T. And we know We don't know Q. We know the mass. We were told the density is 1.00 grams per milliliter. And we know that we have 50 milliliters of solution because we have 25 milliliters of HCl, 25 milliliters of NaOH. So I have 50.0 milliliters of solution. And I know that for every 1 milliliter, there's 1 gram. So that'll give me 50 grams. So our mass for our Q equation was 50.0 grams. We were then told to use a specific heat of 4.18 joules per grams times degrees Celsius. And then we were told the temperature change was that it increased by 7.5 degrees. So from there, we'll now multiply these three together. 50 times 4.18 times 7.5. And from there, we get that Q is equal to 1,567.5 joules. I'm carrying a few extra sig figs right now. I'll re-round to the right number back when I get to the answer at the end. So, from here, we now know that delta H is going to be equal to 1,567.5 joules divided by 0.00250 moles. Remember, the idea is we want a generalized enthalpy for this. We want to know what it's going to be for the reaction without worrying about how much material we have. That's how we do this. We find out how many joules per mole there were, or many times how many kilojoules per mole. So right now we just have how many joules were generated from 0.00250 moles of reactions. So I need to see what happens now when I want to get per mole. That way it's a more useful standardized unit. 1567.5 divided by 0.00250. From this, we're going to get that the enthalpy change is going to be 627,000 joules per mole, or it can also be written as 627 kilojoules per mole. Either of these would be okay. I don't care what you answer as, unless the problem specifically asks for a particular one of these, or if it's a multiple choice, obviously you need to pay attention to your units. Don't accidentally answer that it's 627,000 kilojoules per mole, or that 627 joules per mole. That's a silly reason to miss something. It happens, though, if we're not paying attention. So, that's what we need to do for that one. Now, I'm going to leave the work up because the second question is related. So we ask, assuming that the only reaction that occurs is this HCl plus NaOH goes to NaCl plus water, if you were to accidentally use 25 milliliters of 10 molar sodium hydroxide, how would that affect your enthalpy calculation? Well, in this case, it's not going to do anything at all. Remember, we have a limiting reagent problem. So nothing in the problem changes the concentration of the hydrochloric acid. So if I had much more concentrated sodium hydroxide, I have way more moles of NaOH, but I'm still going to be limited by my moles of hydrochloric acid. So assuming no other reactions occur, the same reaction happens, the same amount of energy change happens, I get the same enthalpy. So nothing's going to actually change for question 2. Now let's look at question 3. It's using a different reaction, so we'll clear this away. So the enthalpy of combustion for methane is negative 818 kilojoules per mole. So it's going to release that much. How much energy is associated with completely combusting 100 grams of methane? So we know we have 100 grams of methane. So one thing we remember, right, is that we want to get towards moles if we're going to try to use this over here because, I forgot to put the 0.0. There we go. So we have the right number of sig figs. Because our kilojoules per mole for our enthalpy has a mole in it. It doesn't have grams. We don't have kilojoules per grams. So the first step is going to be to convert this. And we get that there are 16.05 grams in every 1 mole of methane. We also know, and I'm going to go ahead and do this in 1 step. If you do it in 2, that's okay, that for every 1 mole of methane we combust, we are going to get a total of minus 818 kilojoules. Because we're told that's the enthalpy of combustion for methane. So we know that for every methane mole, we're going to get this many kilojoules out. So if we go and do the math for this, we have 100 divided by 16.05 multiplied by negative 818. We are going to get that our energy associated with this was negative 5,097 kilojoules. So that's how much energy we had. You could also convert it to joules, which would be a fairly big number. You'd probably have it in scientific notation. So that's how much energy is going to be released. And I kept the negative sign with it because it specifically asked just how much energy is associated with it. So that word doesn't tell me anything about changing a sign. It just wants to know what's the energy value for it, whether it be positive or negative. So I left it in the units that it was. Okay, let's now go to our last question, a Hess's law question. what is the enthalpy of combustion for ethane if you know the following enthalpies of formations? And I give you the numbers for the formation of ethane, the ethane molecule, formation of water, and the formation of CO2. And I also give you the balanced chemical equation. So we know that ethane plus 3.5 oxygens goes to 2 carbon dioxides plus 3 waters. And as I commented on my slides, yes, there's a half molecule in it. No, you don't see that in normal balanced chemical equations, but it has to do with how we're writing enthalpies, so that you know if you've got an enthalpy of formation for C2H6, it's for exactly 1 molecule, rather than for 2 molecules, which is what you would see in a more standard balanced chemical equation. So if you remember from Hess's law, I need to take into account everything that I'm breaking apart and everything I'm forming. So if I want to find my delta H for this whole reaction, this will be the delta H of combustion for C2H6. I'm going to know that I had to break apart 2 molecules, well, 2 types of molecules, more of one than the other. 1 ethane molecule. So remember, we have enthalpies of formation. So the enthalpy of breaking it is going to be the opposite sign. So for the C2H6, we're going to have 84.7 kilojoules per mole. Now when you get to the oxygen, remember oxygen is its simplest elemental form. So this is just going to be plus 0. Doesn't show up. Now we're done with the left side. That's the one where we have to change the unit, the sign, because there's an issue of we have enthalpies of formation, but these are molecules you're breaking up because they're reactants. Since they're reactants, you won't have them anymore. So now we go to the products. What are we going to make? So we're going to make 2 moles of CO2 when we do this reaction. So for each molecule, we make 2. So for 1 mole of reactions, we make 2 moles. So remember, we are going to have, first we'll put in parentheses the fact that there are 2 molecules being made each time, or 2 moles, if we're doing a mole of reactions. And then we're going to multiply that by the enthalpy of formation, which for CO2 is negative 393.5 kilojoules per mole. We are then going to add to this that we have 3 waters being made, 3 waters, and that they have an energy of negative 285.8 kilojoule. It accidentally went to my next slide. Sorry about that. 285.8 kilojoules per mole. Kilojoules per mole. Okay, so now we have our delta H for our combustion is going to be equal to 84.7. We're then going to we're going to have 393.5 times 2. That'll give us negative 787, as long as you remember the negative. And you also have 285.8 times 3, which you got to remember the negative 4, which is negative 857.4. So we end up with, let's write that down. So we have 84.7 kilojoules per mole. No multiplication or anything to worry about there yet. We're then going to subtract 787 kilojoules per mole. That's for the CO2 that we're going to form. And then we're also going to subtract 857.4 kilojoules per mole. That's going to be for our water. Also, there's still a 0.0 here. Then we're going to find, once we add all of these together, let's do that, 84, make sure the decimal's obvious. My pen didn't write it very well. 84.7 minus 787 minus 857.4. From there, we're going to get that the enthalpy change for this reaction for the combustion is that it releases 1,559.7 kilojoules per mole. You'll also notice that while this may look like it might be too many sig figs, that this problem is an addition-subtraction problem. So we are counting decimals, not number of significant figures. And for that, the decimal that was the least amount was our tens digit. So, or tenths, sorry, other side of the decimal. So we have to keep the tenths digit, the first one over from our decimal.